Hello, everyone. Thank you to our Olympus tube testing inspection webinar today. I have Terrence Burke from our Quebec factory who's going to be running through this webinar and presentation for us. Just a few housekeeping. If you would like to have a chat or say anything, you can feel free to in the chat bar on the right-hand side. And underneath the screen, we have a Ask a Question. Feel free to ask questions throughout the presentation, and we will address them as we go. Terrence?
Thanks, Graham. So as Graham said, my name is Terrence Burke. I'm in the Quebec factory here working for Olympus as the applications expert for tube testing. So been here over 5 years or so.
Terrence, your mic seemed to have cut out here.
What?
Your mic cut out there.
Sorry about that. Technology, gotta love it. So yeah, if you have any questions, feel free to ask in the ask a question section. We'll get to them when we feel it's appropriate. We'll have and we have a presentation. So we'll start with the presentation. Mic cut out again. Great. Awesome. Might not work. All right, give me a sec. I came prepared for an option B. Give me a quick second. I'm not quite sure what's going on. I'll be right back.
It just started working again there, Terrence.
Oh, I know, but I'm gonna swap mics. I'm gonna see if I can't get rid of this issue. All right, now I just got to figure out which one isn't the USB I'm not using. Oh, wait, I got a free one here. Okay, let's. I'm connected on the network here. Let me see if I can't fix the network as well. So that's okay. That's okay. All right. So we'll try this again. Okay. Is it better right now? Oh, good. Yes. All right. There you go. But there's a delay. Well, better than nothing. Okay. So as I said before, we have 3 sections of this machine instrument. So we have eddy current array. We have eddy current TEA, so regular eddy current, 4-pin Amphenol, standard in the industry. In the next column, we have RFT, which also takes over NFT. So RFT is remote field and NFT is near field. Those are good for ferromagnetic applications. We'll see all this pretty much later. We have MFL, which is also very good for ferromagnetic materials, usually anything with fin fans. It's a good option. Then we have an input-output here. And up top, we have B and C connectors for IRIS, so internal rotating inspection system. In this case, we have 8. Most instruments, you don't need 8. You just need 1. So you would only have like these 2 there. Okay, so that's the instrument. I'm going to try and bring it back to life because it's acting weird, but whatever, I can wait. All right, so step 1, we'll go through the presentation. Now that we got the sound fixed, if you have any questions, hopefully tell me. By the way, I don't see the screen, so if there is a question, feel free to stop me, Graham. Just tell me, oh, got a question, and I'll stop.
Of course.
All right, so tube testing, a quick guide to tube testing. It's a presentation I've done a few months back, years back anyway, but it's all good. So we're going to look at a quick start. So how do we get started from Multiview? You know, that's basically the agenda. I'm going to look at what we can do with this. I'm really here to answer your questions. That's why I'm really interested in knowing where you're having issues, what you want to inspect, and, you know, have a good discussion back and forth. So when we're doing tube testing, this is what we're looking at. So we're looking at regular tubes right here. So regular tube testing. This is eddy current. Here we have iris. You can tell it's iris because there's water splashing from the rear. Over here we have probably NFT because these are fin fans, TRS, RFT maybe. And over here we have boilers. So this poor guy is inside a boiler. It's quite the job. It's not an easy job, but someone's got to do it. And usually it's the youngest person on the team. So you know, you do that for a few weeks and then a few months, and then someone else comes aboard, and then he or she is going into the boiler. So it's good news, right? Advancement. All right, now why should you do tube testing? Well, basically it's because you never know, right? I mean, you have 2 liquids or 2 airs, you know, 2 liquids passing in front of each other, going back and forth, trying to cool everything off. And as soon as you have either a dent, like in this case, this will be dents, or corrosion, you know, this is extreme corrosion. Here you have basically defects around the support. Well, your entire exchanger becomes less efficient. And in some cases can start polluting your 2 liquids, right? If you start getting that mix, that could be bad. You don't want that. So you should always test it to make sure that 1, your heat exchanger is efficient, and 2, that you're not destroying your, you know, your entire process, you know, like your inside the factory. So we're looking at this today. These are big exchangers. At the same time, I mean, think about anything HVAC. You know, even like a small air conditioner would be a heat exchanger. So, you know, yes, we're looking at these big giant things, but you can also have very small or smaller heat exchangers. And in many cases, they'll suffer from the same type of corrosion or, you know, same type of um, um, destructive environment. So really important to check. Now, how often? That's always up to you. That's up to the inspector. It depends on what's going through. Depends on previous experiences. Sometimes people do them every 6 months, sometimes once a year. Sometimes once every 2, 3, 5 years. You know, it really depends. So there is no real good answer. It really depends on what's going through your exchanger and how likely it is to be destroyed or suffer damage. Like in this case, clearly this one suffered exterior damage. You know, something probably hit the shell at full speed and create all these dents, which then make all of these tubes completely useless because, you know, nothing's going through it properly anymore, right? All right. So a few of in-service issues that we've seen. So wear the support plate. So what happens when you have a non-ferromagnetic material next to lying around or like lying on top of, or actually not being lying, it's being surrounded by carbon steel. Carbon steel wins. So if you have vibrations, you have anything like that, it could create wear around support plates. Here it's failure due to steam. So this is just a lot of humidity getting there, eating away at the material. Internal pitting, so this you have to remember, this tube was cut in half, so just internal pitting. Sometimes that can occur if you have in your process, let's say if you didn't filter everything out properly, right? You have microparticles, you can start rubbing all of this, just like sandpaper, right? We have tube to tube wear, so if your tubes are too close and they start rubbing against each other, they're going to start filing themselves down. So those are just like a few things that we look at. Basically what we look for would be holes, pits, grooves, internal grooves, external grooves, and tapered wear. So this would be almost like more of a taper wear. This is a hole. This would be pitting holes as well. Okay. All right. So why the MS5800? Well, the reason is that it does almost everything. I mean, once you know how to use it, it does what you need it to do, right? So it does ECT, which is for non-ferromagnetic material. It does RFT, NFT, MFL. That's for carbon steel, so anything ferromagnetic. And it also does Iris for, once again, mostly carbon or carbon steel, ferromagnetic material, just because ECT does such a good job with the technology, with the fact that it actually removes the support signals. It does a really good job at finding almost everything without the need of Iris. Iris comes in especially as a second step. So you're basically inspecting carbon steel. You know, take a very basic example. Carbon steel, you're inspecting. RFT detects volumetric losses. So you're not really, you don't know if it's on the ID or the OD, right? But you're scanning, you're seeing issues. So in some cases, some people, some owner-operators, some owners want to know more. That's when you would bring in Iris, right? So Iris will give you a full wall thickness inspection. You can start differentiating where the ID defects are, where the OD defects are, and so forth. With NFT, which is near field, which basically you're just looking inside the ID of a carbon steel. So you don't get any information on the outside, okay? Because you have this lack of information, it's always interesting to maybe get a better look. So you use Iris to see on the OD, right? Here, being in North America, we don't really think about NFT as a bad way of doing it because, you know, it does a good job, right? Because we live in a very freshwater friendly environment. When I went to Australia, they can't use NFT. They use either Iris or MFL because all the salt water around, right? There's so much salt water that it creates salt deposits between the fins, and before you know it, the fins actually start to really get banged up. Like the OD just starts to get really damaged. So, you know, what they like to do is use Iris and NFT, right? So they'll go through NFT once, they'll see what's going on. For the really bad tubes, they'll do Iris as well. And in some cases, they use MFL. So MFL is another method to test for ID and OD defects on carbon steel. It's basically you're saturating the wall with a magnetic field, therefore nullifying it, like the natural occurring magnetic field, or, you know, like that attraction that carbon steel has to magnets, it gets rid of it. And then we're using different coils to see what's going on. So if you're properly saturated, you're actually getting ID and OD defects detected. So MFL, another popular way if you have anything with fins or anything like that. Now, the reason I keep saying fins with NFT and MFL is that RFT, unfortunately, as soon as you hit the fins, you will lose all of your signal. So a remote field with anything with fins does not make any sense. Okay. And the last method is ECA, so eddy current array. Basically, the advantage of ECA over ECT is, by the way, I really apologize. My camera on the MS5800 is slow, and for some reason, it's just my hand was not around the instrument. So if you see anything weird, I apologize. I just realized that there's a heck of a delay with it. So ECT versus ECA. Main difference, ECT, you're looking at squiggly lines. Best way to say it. While ECA, you actually get a C-scan. So if anyone here is aware of UT phased array and all that, C-scan is basically a nice image, right? It gives you, it's color coded depending on the amplitude and everything. So it gives you a much more visual way of analyzing what's going on in the tube. Okay. So as I said, complete solution. It has its own software, the Multiview software. You can use Tube Pro if you want to build exchanges beforehand and stuff like that. And as well, Olympus, we supply almost every probe you need. I say almost because, I mean, we stop at a certain size. At a certain size, we're just like, look, we can't do this. We can't test it. And we're not a company that likes to build something and then not test it and send it off to the client, right? So there are limitations, but about 99.9% of the time, it's fine. We also have accessories, so adapters, even the calibration tubes in some cases, we can get those. All right, Multiview ease and use of, and it's ease of use and it's reliable. Okay, it's an easy setup, and there's a few tools for fast analysis, which we'll show later. It's been field proven. I mean, this thing has been around for almost 20 years, and it's still going strong. It works. It's a beast. It's a tank. It's heavy. I know heavy is maybe not a good thing, but I've seen these things being dropped by accident. Of course, no one drops these on purpose because, you know, if you want to keep your job, right? But I've seen these things come in with like huge dents, and they still work. You know, so it's rugged. We'll put it that way. And of course, like you have the Olympus brand name, which you have global support. You have the service center. You got people like your sales reps, like me, always willing to help. Okay, so I'm just gonna go through the options real quickly. We have the E, which is anything that's eddy current, right? E for eddy current, including the ECA probes. R for remote field, near field, and MFL. So R for remote field, which basically we should be, if you think R, you think carbon steel. And then we got the 1U for iris. So U being for ultrasound, and 1 for the amount of channels. So the one you see on screen is an 8U. The reason we made the 8U was when the MS was being developed and conceived, it was replacing another machine, another instrument, which had 8 channels. So it was like, well, let's keep the 8 channels. And then finally, this became more of a tube testing instrument, dedicated to tube testing. So we're kind of like decided, well, the 8 is overkill, and we brought it down to 1U. So a full kit would be ER1U, and that would allow you to do all of this. Okay, cool. So that's the instrument. All right, great, cool, awesome, right? But where, when, how do I use it? Okay, so this is a quick reference I like to show people. It's in the catalog, which is available online, I believe. And it's just interesting because it's almost this easy, right? So step 1 is you select your material, right? Doesn't matter who you work for, whatever. If it's your own exchanger, if you're doing this for a company, yourself, whatever. The first question is, all right, what's the material I'm inspecting? And then just knowing what material you're inspecting, like in this case, aluminum, brass, copper, anything that's not ferromagnetic, right? Well, you can either go to iris, which excellent resolution, C-scan imagery, and the text sizing capabilities. That's great. Tube needs to be extra clean, so there's a bit of a downside too, like eddy current testing. There's always like a whole bunch of limitations. You're always like playing within like the, you know, the triangle. I don't know if you know what I'm talking about. Like if you pull too much on one side, you lose more of that aspect. So there's always a few things you have to keep in mind. But what's really interesting is over here. So you can go straight to ECT if it's non-ferromagnetic. You know, whether it be 304, 316, whatever. If it's stainless steel, copper, you go straight down to ECT. And the interesting thing is that ECT is like the best method because it's quick, it's painless, you get excellent detection and sizing, and even around like supports. So super easy, super quick. Everything has to be cleaned, eddy current a little bit less. You know, as long as you can put the probe in and out, it works pretty well. Then we also have the issue of, all right, what about mildly ferromagnetic materials, right? Like mono, 400 series, duplex stainless steels. Once again, iris works everywhere, okay? But iris takes a lot of time. So if you can avoid iris, you can try either ECT saturation. So what that means, we have a magnet inside the probe, and you're just trying to nullify the naturally occurring magnetic field. So TO probes, those are only good to about a wall thickness of 1.5 millimeters. So sometimes if it's too thick, we don't recommend it, but you can use RFT at a high frequency at 15K, 15K being 15 kilohertz, and that will allow you to inspect mildly ferromagnetic material. So, you know, we always have options here. And then last but not least, anything that's ferromagnetic. So carbon steel, nickel, 400 series, chromoly, iron. We have, once again, iris. As you can see, there's a running theme here. Iris can do everything. But you can also use RFT, okay, which has a pretty good pulling speed. It allows you to size volumetric defects and near field. So near field, it always depends if you have like fins. Anything with fins, you're going NFD or MFL. That's it. That's all. But once again, they're ferromagnetic, right? And I've mentioned a lot of fins on ferromagnetic materials, but in copper, sometimes you'll have fins on copper, right? Well, that works too. You know, you can use TEA probes or EC probes on anything that has fins. Depending on what you're trying to find, you can use a standard probe with just like a bobbin probe, or you can get the specialized TEC probe, which actually has pancakes, which helps you detect circumferential defects, right? So once you have this in mind, it really helps to figure out, all right, what's the next step? Okay. And then over here, we have a nice little chart. Basically, what we can detect, what we can't detect, right? So ECT, we have the internal pitting, that's easy. External pitting, that's fine. Axial crack, that's fine. Circumferential cracking, we have a yes and a no, or actually a poor, no detection, unacceptable. So this is because the way that it works, right? A natural occurring eddy current will not find circumferential cracking unless you're using like a pancake coil, then you will. So that's why we have a no if you're using a standard probe, and yes if you're using a TEC probe, and everything else. So you can see ECT, as I mentioned before, does a pretty good job. Everyone seems to be happy, and this is acceptable if you use the right probe. In RFT, you have internal pitting, external pitting, axial cracks, not really, circumferential cracks, not really, unless they have a huge volume, right? Like, and after a while, like when does a crack become more of a pit or a groove, right? So you got to keep that in mind. Internal corrosion, same thing. External corrosion, super easy. Anything under the TSP is like the support plate. It's doable. There are some blind spots, but the nice thing about ferromagnetic material and the way that it gets destroyed or corroded is that it's never like just a pit. Usually it spreads out. So even if you have something around the support, you should get like before, after, and the support. So it's not too bad. NFT is anything internal. MFL does a pretty good job everywhere except for axial cracks. And then iris, once again, pretty good except for axial and circumferential cracks. That's because the cracks are sometimes too thin, right? So the beam just doesn't see it, just can't penetrate and come back. Okay. So ECT for inspection. So basically, when do we use this? How does it work? How fast can we pull? So for conductive and non-ferromagnetic material, ECT, we say non-ferromagnetic because we can use TEO probes. So, you know, conductive, non-ferromagnetic. Pardon me, I got lost in my translation. So anything that's, as we saw before, copper, stainless steel 300 series. It's a very fast technique. On stainless steel, we're going about 2 meters per second. That's a good pace, by the way. If I don't know, if you're not using a puller or a pusher, if you're able to find someone who can pull, let's say 1,000 tubes at 2 meters per second with an average length of, let's say 5 meters, that's a heck of a workout. So, it's a very fast technique. Defect sizing, very accurate with proper use of multi-frequency analysis. So what I mean there is, we'll see it later, but when you're doing eddy current, you're using 4 frequencies. You're using an F180, an F90, an F90 divided by 2, and F90 divided by 10. They all have their purpose. Rapidly, the F90 is the one that gives you 90 degrees between an ID defect and an OD defect. The F180 is higher frequency, so less penetration, gives you more of a ID kind of a read. It gives you a better idea of what's going on in the ID. F90 divided by 2 has more penetration, so that's a good way to look at supports. As I mentioned earlier, we can remove the support signal using mixed channels, so you want to try and use that, right? If you remove the support signal and there's a defect under the support, well, you get to see it on the mixed channel. Okay. Then we have the F90 divided by 10, which is just what we call the locator. Now, the locator is, if you have a defect, it has to respect the physics of the application. So the physics of the application, as I mentioned rapidly, is an ID defect and an OD defect have 90 degrees in between, right? So if you're changing frequencies, so lowering the frequencies, your interval or your range of that angle is no longer 90. It might go down like to maybe 60 degrees. So if a defect is a defect, it has to follow that natural occurring phase shift, like that closure, right? Now, if you're taking F90 divided by 10 and you realize that your defect is not moving, well, then it's not a defect, it's something else. Sometimes you can get deposits, you can get other things going on in the exchanger. So it's a good way just to figure out what's going on, okay? You can tell if the defect is ID or OD using phase. As I mentioned, 90 degree separation. So we put the hole at 40 degrees. So anything that's below 40, for example, let's say we go from 20 to 40, that could be ID. Then from 40 to 110, that would be OD. Super easy. That's all you need. We have the axial positions can be located, or at least estimated. I should say estimated using landmarks. So if you're able to say what every 5 meters is a landmark, you can start putting a whole bunch of information down and you actually get a good idea of where everything is. So that's important, especially for people who are doing analyses of the exchanger. The reason being is that if no one's going to really remove a shell to try and fix a tube, you might pull the tube, plug the tube, that's about it. But for someone who wants to see what's going on with their exchanger, especially owner-operators, well, that way they can kind of see where all the defects are. So imagine if our defects are where the input of one liquid that goes into the shell and everything is being damaged there, when there's probably something wrong with the process, right? So they will go back and look at what's going on. Maybe they're not filtering enough and stuff like that. So it helps you understand what's going on. And then, as I said, we can size under support plates using the mixed channel. So as I mentioned before, this is the eddy current. So we got what the bobbin probe looks like. Basically, these are the bobbins. They create a magnetic field, right? And that magnetic field creates the eddy current. And as soon as the eddy current is disturbed, we get a reading on screen. So that's what we're looking at, okay? I'm going quickly. Any questions so far? All right.
We don't have anything yet.
So we spoke about eddy current. Might as well show you the eddy current array. So this is the main difference with eddy current array is we went from two bobbins to basically pancake coils, right? They're absolute pickup coils. They have excited coils, and they're actually able to give you a nice C-scan right here, right? So here we have the support, and we know it's a support because of the way that the signal is the opposite of everything else. So this method allows you to give a nice visual aspect. So in cases where you want more detail, instead of just like squiggly lines, which I'll show you later, this is a nice way of getting it, right? So if you're doing non-ferromagnetic material, you want to get more of an image, more of a feel for what's going on. This is a good way of doing it. So without using iris, you're able to actually detect your defects without using iris, which is an advantage because iris involves a lot of water, a lot of setuping, right? In this case, it's almost using it as a TA probe, but with a different setup. So really interesting. No multiplexer needed, meaning that this configuration works without any accessories. We just plug into the 41 pin and it works well. We get C-scan and we have 8 channels. Okay, and we also have the mix, so we don't lose the mix, which is also interesting, which means that yes, here we see the support, but when I'll show you like other images, we will lose the support and it's fine. We can actually see underneath it. Okay. All right, now we're moving on to remote field inspection. So this is completely different. It's no longer eddy current because what we're doing is we have an exciter coil and we're generating a magnetic field, right? So it's good for ferromagnetic tubing. Okay, it's very sensitive to volumetric defects. So anything that has volume, right? It can detect pits, and it has a relatively decent scan speed. It's a bit slower because of you're generating a magnetic field, and basically that magnetic field is going through the wall once, then it's basically moving along its natural line of its natural occurring magnetic field, if you will, and then it goes back through the wall and then into a pickup coil, right? So you can imagine that this takes time, right? So if you're moving too fast, well, you might not get the right reading. So you gotta go a bit slower, but this is what's going on. All right, and usually we keep the distance between the exciter and the pickup coil is usually between 2.5 and 3 times the OD, so the OD of the pipe, of the tube. Meaning, bigger the tube, bigger the probe. It's automatic. The biggest one I saw was, I think, was about 68 millimeters, which give you a lot of distance here, and just the calibration tube that came with it that the client had done was gigantic. It was impressive, because it actually worked. It worked really well. It was just like king size, so it was pretty interesting. So we have different types of RFT probes. We have the simple exciter, we have the double exciter, we have a double pickup, right? So the interesting thing between a simple and a double exciter, right? A single exciter is super easy to analyze. It's head and shoulders, right? So when you see a defect, you basically see the head, and then you see the shoulders, and that's it. Now, the main downside to a simple exciter probe is when you go through a support. Because as soon as you go through a support, the support absorbs all that magnetic field and gives you nothing on the back end, right? So if you're going through a support, if you're going in the right direction, if you're going into the, you're going, well, basically what happens is you're going pickup and then exciter, right? So as soon as the pickups enter the support, you lose it, okay? So you're going to lose all the information on the support, but as soon as the exciter is a little bit out of the support, you get to see the data again. So that could be problematic, especially if you know that you have a lot of defects around the support, right? So what we did is we created a double exciter, and what that does is it creates a less of a dead zone around the support, so you can actually see supports on the front end and the back end at the same time. Okay, and then we have the double pickup. This is mostly this is used just for the 2 plates, like the big thick plates at the beginning. So it's a very specific probe with very specific task at hand. Usually you'll either be using a simple exciter or a double exciter for RFT. Okay, so once again, RFT, we're looking at carbon steel, nickel, anything that's ferromagnetic. Okay, so then we have these beautiful tubes right here, the fin fans. So in this case, we're using a near field probe, which is the same type of technology as an RFT, but used a bit different. So instead of being really far apart, we jammed everything together, right? So the magnetic field just floats on the ID, right? It's just there, right? And then you have all your pickups all around. So it's a very fast technique, 1 meter per second. If you know that you're not looking on the OD, you can use this probe. You scan. If there's anything that seems odd or intense, you can always go back with iris. So NFT is really good for that. Now, however, NFT is also kind of, its downside is that as soon as you lose about, or you find a defect that's about 60% wall loss, right? It won't go much deeper than that. So if you find anything that's below 60, you can actually see variations in the amplitude of the signal. But as soon as you go over 60, let's say if there's a hole, well, a hole in a pit of 60% will look the same. So sometimes on the really bad looking tubes, it's ideal to go back with iris, right? Or what I learned recently, some people go back with a boroscope. They'll just go in to just see what it looks like if there's a hole or anything like that. They won't go back with iris. They're like, well, this one's pretty bad, and they'll use a boroscope and they take a look at it visually, and that works out pretty well. Okay. And this uses the RFT connector, so we put everything on the same kind of like connector, same technology, right? The generator is the same, except physically the coils are closer. All right. So in this case, now we're looking at magnetic flux, right? So carbon steel with fin fans. So this is used to inspect thin carbon steel, oil coolers. It's a fast inspection as well, so 0.5 meters to 1 meter per second. It's a detection probe. Sizing is very limited as sensitivity is proportional to pulling speed, pickup coils, that can be achieved with experience. So, you know, if you've been using these probes for like a year, 2 years, you're getting pretty good at it. You know, you're doing a pretty good job at sizing. If you're just starting, you're getting an idea of what's there, but you really can't size. So you might want to use iris if you want to get a right sizing, if that's necessary for your application. It's very good at detecting ID pitting, good at OD as well. It's good, like I said, if it's saturated. Pardon me. Pardon me about that. So it also detects circumferential cracking, right? And what's interesting is you have what we call the lead pickups. This is differential. Differential pickups are good for small defects, right? And underneath that, you have an absolute, so just a single coil, which is meant for longer defects, kind of a deal. Okay. And what happens is because we're saturating the material, right, the wall, we also have these trail pickups. And what that means is that if you have any residual magnetic field as these pickups are passing through, it means you can start distinguishing if it's on the OD or the ID. So if there's any magnetic field left, it's mostly on the OD. So that's how you can start understanding if your ID is if your pitting is on the ID or on the OD. Okay. All right. Last technique we're looking at is the iris, the internal rotating inspection system. So used for tube having a wall thickness of greater than 1 millimeter. It's accurate defect sizing because you're using ultrasound. It requires very good tube cleanliness, and tubes have to be flooded with water. That's one of the major downsides to iris is you need to flood these tubes. It's a powerful backup technique to RFT, MFL, and NFT. But it's a very slow inspection speed, 5 to 10 centimeters per second. So what's interesting here, right, is you basically have a transducer here, which is beaming onto a 45-degree mirror, which is rotating. And what happens is the beam gets diverted towards the wall, and then bounces back to the mirror and bounces back into the transducer, right? So this thing is spinning, but because the speeds are so fast, like for example, I think the speed of water is 1400 meters per second, and then steel's like 54 or so, 5400. So it's really fast, right? So even if you're spinning at about 30 to 40, 50 rotations per second, you're still getting all that information back and forth. So it gives you a really clear signal. Okay. However, you have to remember this is completely flooded, so there's water all over the place, and the other thing is you need setting devices, right? So we have setting devices that go up to about 76 point, I think it's 8 millimeters. After that, we can't do anything bigger, right? That usually covers a good spectrum, about 90% of like every Iris application. But we do have limitations, and Iris is also finicky. It works. When it works great. Sometimes getting it started takes a little bit of takes some TLC, we'll put it that way. But once you got it, you got it. In this case, it's really important to make sure that when the tubes are clean, that your calibration tube is also identical to what you're using, and just to make sure you're getting a good idea of what's going on. Okay. So Iris, the main advantage is this. It's a beautiful
Hey, Terrence, we do have a question here, if I can throw this your way.
Hello?
Hi, can you hear me now, Terrence? I do have a question for you.
Yeah, give me a sec. I can't hear you. Can you hear me?
Yes, I can hear you.
All right, that's weird. I'm using two headsets now. All right, go ahead. What's the question?
So what level of operator skills are required? Technique of limitations and disadvantages and extent of tube clean is required. And what type of cleaning method is suggestible against each technique? How to ensure cleaning is sufficient or not?
Okay, all right. All right. So for the levels, right? A level 1 can do basically eddy current basic testing. All right, like anyone can do it. Ideally, it's level 2, and if you want to be really secure, you find yourself a level 3, which is not necessarily easy. But a level 1 needs to be chaperoned by level 2, but level 1 can do the job. Just level 2 needs to chaperone and say, "Well, you did a good job. Congrats. Here's your signature. You can move on." Okay, so that's what's going on first. I don't know if anyone here has done their eddy current course. When I did mine in level 1, you're mostly doing surface inspections, like pencil probes, surface probes, stuff like that. And when you get to level 2, that's when you start seeing tube testing. So, level 2 for signatures and all that, and just like having someone who understands what's going on. But I truly believe a level 1 who tries can learn it, get to level 2, and move forward. It always depends on your business, on how you want to keep that involved. Okay, so that was the first one. What was the second question? There was like a few of them.
So technique limitations and disadvantages, and then there's the extent of tube cleaning required and what type of cleaning method is suggested for each technique.
Okay. All right. So advantages, disadvantages. So with we'll start with Iris, because that's what's on screen. Disadvantage of Iris is the amount of water that you necessarily need. The amount of components which are needed. So imagine you have a source of water. It can be a hose, can be a bucket with a hose in the bucket. You have a filter, because you want to make sure that water stays clean. Just for, if you, like I said before, it's like if you have material particles in the water, and it becomes like sandpaper at the speed it's being pushed at. So that's no good. Other limitation, which goes for a lot of these technologies, is sometimes if you have anything with bends, like Iris in a bend is always tough, because at a certain point you're not really going, you're hitting a wall somewhere, right? So that becomes problematic. Let me see. Other disadvantage. You got to make sure everything stays clean. So there's a lot of cleaning involved, because anything that soaks in water, even if it's stainless steel or galvanized or whatever, anything that even stuff that's not supposed to rust, if you don't take care of it, something's going to happen. Okay, so that's for Iris. NFT, its main limitation is the fact that it doesn't do anything on the OD. So you're almost forced to do a second inspection, whether with Iris or MFL, to get like a better understanding of what's going on. MFL has kind of like the same. MFL, the biggest disadvantage is we don't know if the wall is saturated or not, right? Imagine if you think the wall is saturated, you start scanning, you start marking tubes down as these are great, these are awesome, and then someone goes back with Iris and sees a whole bunch of defects on the OD, right? Well, that's because the wall wasn't saturated enough. So that's always a risk. I recommend people calculating it. If you wanted more information about that, That's for a different meeting, or just send me an email. I'll send you some stuff you can look at. No worries. But that's one of like the biggest downsides to that, like for me, to that application. Remote field. Remote field. One of the biggest problems with remote field is that it's hard to analyze. Like if you're using a TRS probe, it's not too bad. If you're using a TRX, which is double exciter, so TRS is a single exciter, pardon me, a TRX is a double exciter. Well, in the TRS, you have like the head and shoulders, which is kind of easy enough to see. But if you're using a TRX, you have head, shoulders, toupee, and then everything goes back down, right? So there's a lot of information. Sometimes, like if your defects are very close, they start merging together. So it's kind of hard to get a really, accurate differentiation between what's going on. It works well, but then you have to remember if your defect is longer than the probe, and it's going through 2 times the wall loss, what happens to the signal? It's twice as big, right? So then you have to remember, okay, wait, this is a long defect. This looks like a long defect. Therefore, the max height has to be half of that. Then you have to calculate the half, and not a bad technique, but you're asking for disadvantages. So that's a lot of like extra analysis that has to be done, right? Luckily, so far so good. It's all like physics-based limitations. It's not an instrument. Doesn't matter who makes the instrument, you'll end up having the same issues. And then for ECT, ECT is actually pretty decent as long as it's non-ferromagnetic. As long as you have a good calibration sample, everything goes well. I'm trying to think of a major disadvantage about ECT. I'm almost preaching to the choir here, but I'll think about that one a bit more. I'll start with the easy ones. Oh, and also for Iris, it's the scan speed, very slow. So because it's a slow scan speed, it takes a long time, right? All right, and now for cleanliness. The cleanliness methods, I know all you need to do is basically water blast the tubes. For eddy currents, usually enough with a certain PSI. I forget what the PSI is exactly, so I don't want to just make up random numbers. I don't like doing that, but there's a certain PSI usually cleans it out well enough. So with the way that a eddy current, remote field, near field, MFO probe are made, right? The way that those things are made is it kind of like a pusher nose, right? So even if it's not 100% clean, that nose when you're pushing that probe down the tube, because you gather data on the pull, because the pull is just more stable, more constant. You're able to remove a lot of like anything, like some of the junk and all that stuff. So it doesn't have to be overly clean. It just has to be clean enough that whatever's left can be pushed out by the probe. Let's put it that way. If you have anything that's, for example, if your client says, look, I pass a very high, I pass fluid here and has a high amount of iron, you're going to ask them to make sure it's super clean, as clean as Iris, because if you have iron inside those tubes, right, inside, let's say, copper tubes, by the way, this is a completely insane example, but it's just to get the point across, is those iron fillings could actually modify and warp your signal, right? So usually eddy current, you just have to rinse them up with water. That's good enough. RFT as well, NFL, NFT as well. Relatively easy. When you get to Iris, that's where it has to be really clean, because Iris you'll be flooding, and you want to make sure that there's no crud or crust inside the ID, right? Because ultrasound will not go through air. So imagine if you have like a layer of crust and a bit of air, well, then you're not penetrating through the wall, and therefore you're not getting it. So when you're using Iris, it's always super important to be extra clean, just to avoid any of those type of situations. All right. Did that answer the question?
I believe so here. So next question we have here, we have a couple for you.
Yeah, go for it.
A U-bend, what type of probe can be used for this inspection, and what is the probability of detection?
Okay. So in U-bends, we have the TEG probes, which are So anything that's TE is usually associated to eddy current. So we have TEG probes, which are for eddy current. Detection is pretty much about almost the same. When dealing with bends, right? Usually, where you get most of the corrosion of the problems will be right in the elbow. So you're going to detect that. You'll be able to go around there easily. For remote field, we have the TRG and the TRC probes. So those will go around the bend. Once again, you might get some dead spots, some dead zones, but usually you'll get probably before the elbow and after the elbow, sometimes like right in the middle of the elbow, right in that extra high angular area, you might not get it as well. Okay. Then you have iris, which we have flex probes for iris. Iris is probably the trickiest one because of the way that the beam bounces back. So you'll get before the elbow, you'll get a little bit maybe in the middle of the elbow, and then at the end of the elbow, kind of a deal. Okay. So that's what you're looking at for the bends. Once again, the bends just depends on what material you're using. So if it's ferro, non-ferro, and also there's limitations to the way that the probe can bend around. For example, I think there's a few, like if you try and go around like a 1-inch bend, right? It'll never work with no matter the probe, because at a certain point it just causes too much friction. The head just starts plowing into the bend. It's no longer going around. So what we recommend is you do as much as you can on one side, and then you go on the other side, do the rest, kind of a deal. Okay. Very common application with boiler tubes. People go as far as they can from the top, as far as they can from the bottom, and then they have like they'll have like a general idea of what's going on inside the bend. All right.
Okay. And we have one other question here right now. Tubes with metallic ferrules or liners. How does tube inspection technique will be affected with this, and what is the probability of detection?
Okay, with metal liners, that's what they want to ask.
Yes.
Okay. Well, that's always it's always dependent on what material is there, right? So, for example, like, does the person have an idea of what the liner is made of? Any material?
I do not have that information. Manish, would you like to comment in the comment section if you have a specific liner?
Because what's really important, right, is that when they make the cow tube, they make it as their tubes, right? So if you
It's
have
a
yep.
Hasiol liner.
Okay, all right. I'm not sure what that material is, so we'll try and give a general example. And worst case scenario, I can talk to the person after for more information. So what would happen is if your calibration tube, right, if you're able to build something identical and test it out, then you'll be fine, right? Because what happens when you put the probe in the material and you null, assuming that your liner is thin enough that there's penetration into the wall of the actual tube, well, you'll get like an operation point, and that operation point will vary depending on what you're seeing, right? So where it gets tricky is if your liner is either too thick, maybe has like some ferromagnetic properties, then it's going to start really acting weird, because anything that's ferromagnetic, if you're using even remote field, you might have like some variation and all that. So it just gets a little bit complicated. It's not impossible to use. That's not what I'm trying to say. It is possible. It's always dependent on what your material is, what your liner is, and how thick of a wall you're going through. So for that question, I almost prefer reading up more on that material and getting back to the person. So Graham, if you can just like leave me the information or send me an email at the end, that'd be great. Because like I said, I know it's doable, but there's a lot of not variations, but there's always a few. Man, I forgot the word. Anyway, I'll get back to that one. When I remember the word, I'll tell you. Sorry about that.
No problem. Manish, I'll have Terrence send you an email and we can discuss this offline afterwards. Thank you.
Cool.
Cool.
All right.
And that's all for questions right now. Thank you.
Perfect. All right. Thanks. All right. I'm assuming you can still hear me. Because all right. So this is how Multiview works. I'm not going to go through this because I'd rather show it just to understand what's going on. But basically, what I want to show you is that we have a place that our operation inspection where we save all of our data. And it's important to do this first to avoid overwriting data. And also, if you have like a Carto or 2 Pro, you can load up your inspection list here, and you can also save your report file. So that's really important. We have a wizard. So the wizard is great because if you're brand new to tube testing, it's a good way to get it done. It's the best way to avoid anomalies. You name your setup file, you can give a brief description, you select the technology like here, and then you can just press create, and you get this wonderful little menu which helps you understand, like, all right, pick your material. By picking the material, it picks the resistivity. Then you select your thickness, either manually or using the Birmingham wire gauge over here, which will then calculate your F90. You select the type of probe you're using, what kind of reference you're doing. So that's for nulling. The reference is for nulling. You can have an external reference, which, let's say if you have 2 identical probes, you can leave one probe in the cal tube, or if you're wild, inside the exchanger, knowing that there's no defect there. So you always have like a good balance point. And the type of connector, if you're going through the standard 4-pin or the 41 pin. So doing this will help you get through the rest of the setup rapidly, as then it basically selects, it basically sets your 4 frequencies afterwards. You can select your cal points, your how you're going to calibrate the signal, and your landmarks and everything. So it's really quick, really simple. And this way you're sure it works. And yes, there are ways to modify the setup later on. Like I said, I'll show you when we get to the software, but I just want to get you a feel that the wizard's there to really remove a lot of the stress of what's going on. Okay. And the same can be said for RFT. Same thing. Basically, you select your material. You will select the thickness and calculate the frequency. Usually it's about 300 hertz, sometimes 400, 420, 500, whatever. The really important thing is that it tells you exactly how fast you can pull that material, right? So the thicker material, slower you're going to pull, just because it takes more time for the magnetic field to leave the wall and go back in the wall, right? So that's what we're looking at. We have more RFT settings here. So basically what kind of signal you want to see. If you want the absolute pickup, differential pickup, this is when you have a TRX, a double exciter. So this is what you're looking at. This is the pickup, pardon me, a TRT probe. MFL, probably the easiest setup ever. Since there's no real frequency, it's just a magnet. All you have to say, all you're telling the system is, look, you're just looking for absolute, differential, and trail signals. Gives you the speed at which you can pull, and you can go faster, lower by adjusting the bandwidth. And then we have the calibration. So calibration, there's a whole bunch of different ways you can do it. We highly recommend doing channels and depth curves. Yeah, depth curves are nice because once you're done calibrating your cal tube and you start inspecting your unknown tubes, well, the software will try and help figure out what you're looking at, right? So it won't give you the right answer. It won't give you the wrong answer. It's going to give you an estimate. And this is where it's important to be, when someone's asking about the questions like, what level should you be? But level 1 can do it. Like a level 1, I have no issues with a level 1 doing tube testing. But when we get to places like here, like in situations like this where it takes a bit more analysis, a level 2 really helps, just because they've been there. They have more experience. They've done their tube testing and they've gone to another level. It's essential when you get into like the tricky situations, because the last thing you want is, and look, it's Olympus product. We put it in there to help people, but you don't want an inspector just to rely on the depth curve to figure out what's going on. you got to look at the phase, you got to look at the amplitude. There's a lot of things you have to look at and make sure you understand what you're looking, what you're identifying. So this is a nice way of doing it. What we do with channels in this case is what we do to calibrate a signal. Let's say you have nothing, right? You're in the middle of nowhere. You have to inspect the tube. You can find there's a piece of good tubing next to you. I don't recommend this, but what you would need would be just a hole. If you can pierce a hole using a drill of a certain size without distorting the metallurgical properties, you can almost calibrate anywhere. Okay, because what you're going to do is you're going to calibrate at 4 degrees on a hole and a 1 volt. As soon as you do that, you're good. The rest is overkill for calibration. The rest all goes into depth curves, and also to validate your F90. If your F90 is really at 90 degrees, so you have an OD and you have an ID defect, you just want to make sure they're at 90 degrees, right? To confirm the calculated F90. But if all you want to do is calibrate a signal, all you need is a hole. Just do a hole, and then you're good. So, like I said, there's a lot of extra features in the software which helps you understand what you're looking at. But there's a lot of interpretation that has to be done. Inspection. So this is basically once you're scanning through all the tubes. This is all your tube sheet over here. You're just going to go quickly. I should have turned off my Teams. Oh, sorry about that. Oh, okay. So the analysis, we'll just go through it live. It's going to be a lot easier. I'm just showing you where all the buttons are and everything like that. So that's okay. The report, I'll show you that live as well. Advanced features. So we have scan parameters. These are all things I'll show you rapidly just to get you an idea, but size and sample rates can be changed in the scan parameters. Analysis setup, you basically add, delete defect codes, same thing for calibration points, landmarks, depth curves, all this beautiful stuff I'll show you on the software. ET channels, this is where you're actually able to change your frequencies. For example, your calculated F90 makes no sense. It's not giving you 90 degrees. You want to increase the spread and the 90 degree. You want to increase it. You'll increase you'll change your frequency here, and by doing so, you'll be able to adjust every other frequency. So in this case, we only have one, but I'll show you within the software that you actually have 3, 4 different frequencies you can modify. All right, so that's it for the PowerPoint presentation. Took a little bit longer than expected. I apologize. But if you have any questions, now's your time. If you have more questions, and otherwise, we're going to move over to Multiview and just show you what it looks like. If everything goes well, I'll be able to give you a live calibration on a stainless steel pipe, tube, pardon me. And yeah, so any questions? Anything going on?
No, there's no other questions at the moment.
Okay, let me turn this one off and this one on. All right, so my original plan was to show you the live view of the multi-scan. Unfortunately, it's acting weird with my OBS Studio, so we're just gonna put a pause on that, and I will delete the PowerPoint because I don't need that anymore. It's just being troublesome. Okay. So what we're gonna do now is, so this is the Multiview software. We're going to go here, operation inspection. I'm just going to change this to one. So what I like to do is I like to put all my files in the same spot. It just makes it easier that way. So if I ever need to, whenever we need to do something, we can go like that. Okay. The reason I put the slash at the end is just to make sure that I keep everything in the same folder, right? For whatever reason, I need to give data back to a client, colleague. I can just grab the folder, send it their way, everything's fine. So that's step one. What I'll show you now will be the wizard. So set up wizard. I don't want to save that. I'm going to call this SS316 March 23rd. And we'll be doing eddy current today. I'll show you samples of other data afterwards. So we're going to do something just quick, painless. So I'm going to select the material out of my list. So I'm pretty sure it's 316. My thickness, just going to try and take a quick look. It's about 160 some, so let's go here. 165, it's gauge 16. So now, as you see, have you seen my resistivity has changed, my thickness changed, and my F90 changed. If I bring this to this, my F90 changed as well. So it's basically just doing 3 times the resistivity divided by the thickness squared. So that's how we're calculating the F90. Okay. I'm using a bobbin probe, which you saw on screen is plugged into the 4-pin, and I'll be using an internal reference. So that's fine. So now the wizard's saying, hey, all right, knowing what you just told me about the F90, these are the other 3 frequencies I recommend. So F180 is basically F90 times 2. So 174 kilohertz here, F90 divided by 2, 41, and then F90 divided by 10, about 8. So that's fine. They asked, now the next thing is, what do you want to see? Do you want to see all your differential channels? Like, yes, I do. Absolute, definitely. And would you like a mix? I'm like, yes, I would like a mix. I would like to keep the F90 and, well, D90, so the F90 but differential channel. And I want to subtract the F90 divided by 2 differential channel. So this is what I'm looking at. Now, the reason I'm taking the 90 divided by 2 is simple. That has more penetration, right? So because the eddy current penetrates deeper into the material, it allows me to see the support plates better, and therefore an easier way to remove them, right, from the mix channel.
Hey, Terrence, the wizard is not showing right now.
My what?
The wizard is actually not showing at the moment.
Oh, sweet. That's awesome. Great. Thanks. All right. Everybody here, do you see it?
Yes, we can see it now.
All right. Okay. So that's good. All right. I'll go back and I'll just re-explain. Sorry about that. Thanks, Graham, for the heads up. Okay. So what we have here, right? We go into the wizard. So the you didn't see anything. Screw it. Let's start over. I don't think we're 20 seconds away from this. Okay. So now you see the setup. We're going to call it March. Oh, wait a minute. That means you didn't see everything either, right? Okay. Let me redo this just in case. Yeah. All right. Step 1, when you go into inspection, so you go into operation inspection, is what I like doing is I like putting all of my folders at the same spot. Okay. So I put my save data folder with the slash, my inspection list with the slash, and the report file with the slash. It's super simple, as I said before. That way, if I ever have to give the files or I get audited or whatever, I can just drag and drop the folder. Everything's in there. So step 1. Step 2, wizard. So now we get this nice little setup box. Okay, what do you want to call it? I'm going to call this March 23rd, 316. I'm not going to leave a description. My technology, I'm using eddy current, so that's fine. I'm going to go create. Now, this is what happens. So it calculates the F90 using 3 times the resistivity in microohms per centimeters divided by thickness squared in millimeters. So I'm using stainless steel 316. So calculates the resistivity. the thickness, and here's the F90. Now, my thickness is not right. I'm more around 1.65, gauge 16. So I'm like, all right, gauge 16. See, calculate the F90. The rest is I get to select my type of probe. In this case, it's a bobbin, nothing special, no AC probe with an adapter, nothing. I'm using an internal reference, nothing external, and my connector is 4-pin. Okay, so then this basically calculates my, pardon me, I don't know why people keep calling me. So this calculates the prime value, which is 2 times F90, so 174. The F90 is 82, which was calculated previously. The F90 divided by 2 is 41, and the F90 divided by 10 is 8. So far, so good. I want to see all differential channels. I want to see all absolute channels. As I mentioned rapidly before, differential channels great for pits, anything localized, really small defects. Absolute great for anything that's long. Any long defects, that's what you want to use that. Last is, do I want a mixed channel? And I'm using eddy current. I definitely want a mixed channel in case I have anything under the support plate. So yes. So I go next. So then it asked me about my calibration too. All right. Now, if you're using an Olympus standard, what we call the CT02 series, all those defects are present, right? So for me, it's no big deal. I can go next. Now, if you ever build your own, I'll show you how to change that later in a few minutes. Okay. So in my case, this is fine. I want to calibrate on the whole. I want to get the steel support for the mixed channel, and the rest are basically for depth curves, right? So what I mentioned before, depth curves are to give you estimates of what you're looking at. So that's what I want. I'm like, okay, cool, perfect. Then we have the report codes. The report codes are the codes that go in the report. Duh, right? That was really obvious. Sorry about that. The interesting thing is that you get to pick the channel you see them on, right? So an OBS is an obstruction, which means in tube testing, if you cannot get a full inspection, a full 100% inspection from point A to point B in your tube, forget about it, right? You can't say tube is good, tube is bad. You have to say I was unable to inspect it due to an obstruction, a dent, or it was previously plugged, right? So a plugged tube is, imagine you're in front of the exchanger, and the person before you, or even the inspector before you, before them, realized that there was a tube that was completely finished, so they plugged it up. Either they put a stopper, they welded it shut, whatever, it's plugged. So these are important to identify. Okay, if it's been plugged, it's been plugged. That's all you can say. If you can't inspect it because you hit a dent halfway, you can't inspect it. It's a dent. It's up to the owner to figure out what's going on. And same thing with an obstruction. Okay. Now, for the real defects, you can have pits, and pits are localized usually, right? Small defects. So we're going to say you're going to look for a pit on the D90 on the French channel. These are wall loss long. Now, wall loss would be a long defect, so you're going to look on the absolute 90. So that's why we put it here. A DSI is a defect under the support. So if it's under the support, the only way you can detect it is using the mix. So we're going to tell the system, look, if you find a DSI, it's on the mix. And then a wall loss short, which is the same as wall long. Pardon me. Wow, that was weird. Same thing. We're going to say it's on the A90. And you can also add different types of defects if you really wanted to. When you get used to your exchangers, you start seeing patterns. You might want to start creating your own code and telling your inspectors where to put it on. Okay, and then you have the depth curve that you can use. So we usually use phase. You can also use amplitude or volt depth, but usually we do the phase. Okay. And then last but not least, last page, it tells you, all right, that's great. How do you want to calibrate your signal? So we want to calibrate on the whole. We want to say it's 4 degrees, 1 volt. That's what's in the books. This is how you're supposed to calibrate it. Calibration point here, same thing. So we're like, okay, we're good, we're done. And now it's being configured. Okay, so now I'm good. Here I see my PC and my box are connected. That works out well. I'm going to grab my probe. Step 1, look inside the cal tube. Make sure wherever you null, there's no defect. Because if there's a defect, you're going to change the null point. And change the null point means that you're not going to get the right information. So once you're done doing that, first things first, you're going to balance the probe. First balance is always like the longest, especially when you're starting like the low frequencies. Like we're at 86 F90, so it goes all the way down to 8, which is pretty low, which takes a little bit more time. I'm gonna try something crazy. I'm gonna try and hopefully you still see my screen, right? Okay. So now we have this that says we're balanced. Now we're gonna do our first initial scan just to get some data. That was actually pretty bad. I thought I was out of the tube. Just gonna rescan that pretty quickly. A little bit better. Okay. So, like I said, in this case, my scan looks pretty good. I'm just going to go into my channel calibration. And what's nice with the cal tube is that, like it or not, you know what you scanned, right? I have all the information in front of me. I know that's an ID. I have 2 holes, so that's the big hole. I'm going to use a small hole to calibrate myself on. So I'm going to use this hole, record. Then I'm going to go here. So what I'm doing now is I'm just telling the software what I did and what I physically did. So I'm just saying, well, these are all my points. I'm going through my cal tube, putting them down. This is the 4 times 20 right here. Interesting fact, because you can see the support signal is the opposite. All my defects, if you go from here, go from left to right, left to right, left to right, left to right, and then this one goes right to left. So support signals, because they tend to be carbon steel, have the opposite form, the opposite form than eddy current or defects. Then we got to look at, this is my ID. So that's my ID groove 10%, record, and then my OD20 is right here. And then I'll do this, record. So if I do it once, now I have all my defects going like so. And then I'll just do this one rapidly for the support. And now I'm set. So what that does, right, is if I go here and I load my mix. Actually, let me refresh, that's fine. So I have my mix. So right now you can see that on my D90 as well as my mix channel, we see the support. Okay. Let's see when I rescan what happens to the support plate. So I haven't moved anything out. I'm scanning as it was before. And now I'm done. And it's still there. Ah, great. There you go. Okay. So it didn't work last time. That's fine. Okay. So what it did, right, is now on my mix channel, it got rid of the support. Now you're telling me there's still some noise. Yes, granted, there's still some noise. But overall, it no longer exists. Okay. So now I can go through all my defects here. If I click over here, it tells me what it believes it is. So this one is a big hole. So this one, since it's having issues, it's like, it's a pretty big hole. So it thinks it's on the OD. And it's actually 33.9 peak to peak. So it's like, it's pretty close to 40. So this one would be, this one as an inspector, despite the fact the system says 80, the fact you're at 33.9 is kind of high, and the amplitude is big. So you might want to reanalyze that one. My hole now, which used to be at 40 on the dot, I rescanned. Every scan's a little bit different. You scan a bit faster, the wobble, I mean, there's always a bit of variation, which is why it's important to, as an inspector, to understand this, that, you know, you're at 43.1, you can't be like, oh, this is by 90 some. It's like, well, first of all, if it is 90%, that tube is not looking very good. So you got to be careful about that. And also, you can basically say it's a hole at this rate, you know, it's a leaker. And then as you go through, you're basically getting different readings. As you can see with this, what I call the flower image, is as the defect gets higher or gets closer to the OD, it opens up. It opens like that flower up. It changes the phase. And the reason is it takes longer for the eddy current to penetrate the wall, find the defect, and then go back to the probe, right? So that explains the flower effect here. Now, if we look at the long defects, so right here, that one, these ones aren't too bad, but as you can see over here, let me just load up a mix, A90. So over here on the D90, and you look at the A90, the long defects are huge when you're looking at it from a differential point of view, right? On absolute, because we only put 0.1 volts on the hole, we get to see them easier, right? And that's why we often say we're going to put we're going to look at long defects on the absolute, short defects on the differential, just for that. I mean, here on the differential, they're super easy to spot, you know, like really easy to see. You can almost measure the almost the length if you wanted to. If you had landmarks, you could almost measure exactly how long it would be. It'd be like the minus 6 dB anyway, but because there is like eddy current spread, but you can get a good idea of what's going on here. And once again, your supports are negative, right? So next little thing I want to do, I'm just going to cover up one of the defects so I can show you the effect of the mix. We'll do that again, and then I'll show you. Then, if you have any questions, we'll ask questions. Otherwise, I'll show you some more data. And like I said, if you have questions, we'll answer questions. So now I put the support over a defect. So we can already see the support here. Pardon me, that's not what I wanted. So we can already see the support is right here, right? So I put this on I think it's the 60 I put it on, right? Yeah, 60. So if I look at my D90, it's all messed up. I have a mix of a support, I have a mix of some sort of signal, which isn't a support, all mixed together. On the absolute, it's so small, but as you can see, it's negative, right? They're all going towards the right. This one's going towards the left. So you're like, well, there's something going on. However, there is a bit of a return to the center nominal wall in the middle. So there is something kind of like counterbalancing the support. But right now, I really can't see. So all I do is I go on mix channel, which is right here, and I'll zoom in a bit. And on the mix, it actually sees the defect pretty well. Yes, there's a bit of the noise left from the support, but overall, you're getting a good idea of what's going on. You know, so it's kind of impressive of how the mix channel really helps eddy current to become a really easy technique to use. Because imagine this, right? You have an exchanger, you're scanning, you're going to have a whole bunch of supports, and they're going to be almost constant on the screen. So a lot of the times you'll have almost nothing to say. And then when you start having weird support signals like we have here, you're going to be like, this is weird. I'm going to investigate. And then you start investigating on mix. The same can be said if you start looking on F180, A90 over 2. You see, like, everything changes, right? So you're getting a whole bunch. You're getting a different way of visualizing what's going on by changing materials, by changing channels and all that. So eddy current is a very good technique, you know. And like I said, this I'm using this on stainless steel. Unfortunately, I'm running out of tubes these days. I've had a lot of loaners, but I could be doing this on brass. I could be doing this on copper nickel. I would get the same result if I'm using the right probe, right? And the right probe is just dependent on the material, and the wall thickness. So the resistivity and the wall thickness. So as long as I can find a probe that my F90 fits in that range, then it doesn't matter what I'm looking at. This is what I'm getting as far as a result. Okay. What I want to show you here. So I mentioned if, let's say, you want to use your own cow tubes, you can come here, announce the setup, and you can actually modify them. The reason I show this is, yes, Olympus, we have our own cow tubes. ASME have their own cow tubes that we basically base ours on. But as I said, if, let's say, you're in a rut, you're in a tough situation, or the company who milled your tube made a mistake, you can come here and modify these values to get a better or more accurate depth curve, right? So that helps if need be. And for example, if you only have an ID, an OD, and a hole, you just put that down and you can get everything done. You can also add indications here, not necessary for now. And you also have landmarks that can help you understand where everything is. So what I mean by that is, I'm just going to put some random stuff down here. Put the start here. I'll put something here. I'll put something here. Okay. So what that means is, when now I put all my landmarks down, if I start putting defects, so this is I'm going to go on the absolute. I'm going to say I'll just put that for now. It will give me, if I go into report, it will give me a start position plus the cursor of where it is. And it kind of gives you like an idea of where everything is. So my cursor length, because I did all of this manipulation before, says it's about 0.169 meters, so 169 meters. And so that's what it thinks is the defect. It's not up to size, it's not up to scale, because I did the random thing right now, but it's just to show you that with the software, if you put a bit of effort into it, you can really get a pretty decent report going, and a lot of information can be exported. Okay. Any questions about ECT? I just want to show you like NFT, RFT, Iris, MFL, and then that'll be about it. I hope so far it's going well. I hope you're enjoying this. I know I've been talking for a while, but I just want to make sure that you understand which method is best used depending on what you want to try and find, and advantages, disadvantages. So eddy current, pretty powerful technology when you know how to use it properly. Okay. So I'm just going to load some data files. Okay. So let me see. I have a ECT AC. So I have a bobbin here. I won't save that. I'm okay. So this is a different material, different scan, which was done many moons ago. And it's the same thing as we saw previously. Same type of, it's not the same cow tube. I know that for a fact, because I'm pretty sure this one was, yeah, this one's lower. So this one might have been like brass, I would suspect. So the fact the fact that it stays constant here, that we got the same thing here. We have a mix, which hides better than I did, because it did a better job with it, but it hides the support really well. You have all your defects everywhere that you need, same defects that you saw before. The reason these ones are giving us exact terms is because it was scanned once and they saved the data as is. So the depth curve, which if I go here, the depth curve and what they see on screen is exactly the same, right? So that's A90, D90 is the same. Okay. So you're getting the exact same readings. Like for example, here around the 69.5, and I have 69.49. So that's giving us a perfect 60 FBH. Okay. So really doesn't matter what you're doing. If you're doing eddy current on non-ferromagnetic material, if you have the right probe and you have a support signal, you're golden. If I look at an iris, so an iris on the Cal tube, that's what it looks like. So we have a groove here, a groove there, 4 pits, a deeper pit, and sometimes we have a hole. In this case, we don't. But what you're seeing here is this, I believe, is a 20%, and this is a 40%, and these are 4 times 20s. This one's a 40% hole pit. So you get everything here. You can actually see it on the cross sections here. If I go over here. So we can see the cross sections over here that now we have less material. I like coming here because you really see the OD pits well. And another thing that's interesting, if we go into, where is it? Where is it? I'm going nuts here. Where is my? Oh, here it is. Sorry, my bad. So what I want to show here is basically just the sequential view, right? So if I move this around, you can see that the wall thickness changes. Full, 20% less, about 40, 50% less. And I have my 4 pits here, and then I have my 1 pit here, which was located there. So a lot of like interesting things. So this is nice with an iris scan. Imagine you're doing iris all over the place. You can get nice C scans like this. If you're very well calibrated, you get the right centering device and all that. I'll show you what OD corrosion looks like with iris. So we got data over here. So we can see all the OD, the corrosion over here and so forth. So kind of interesting as well. And then you have like the profiles move and everything with the P scan and D scan. So that's kind of interesting as well. Same here. So we got a lot of OD pitting here. You also have different views. You have the OD view, you have the ID view. So really nothing on the ID. The wall thickness is basically OD minus ID. And the other one is just what we see on the OD. So see all of that. We got different options here to change the color palette and all that. So, depending on what you want to see, you can modify it and so forth. Okay. So iris. Then we have MFL, the calibration. I'll show you what this looks like. So what's interesting too is I'm going back and forth from iris to UT. I can know once I have the data, I can load the data any way I want. So that's really interesting. I don't have to reboot. So I have my absolute over here. So I have 4 long grooves. Then over here I have my pits. And what's interesting is on the trail, I can say if it's on the ID or OD, right? So you kind of have an idea of what's going on here. So this is MFL. This is, like I said, if you can assure that the wall is saturated for anything with fin fans, does a pretty good job. Really popular around anywhere where they have a lot of salt water. Really popular. NFT cal. NFT is the easiest version, easiest technology to calibrate. For some reason, my data is all messed up. There you go. So we have the absolute. So what we have in this tube is basically we have 2 internal grooves and a pit in the middle. So the pit really comes up well in differential mode. Absolute comes out, you don't really see the pit, but you see the 2 grooves. So that's interesting. Other thing is At a certain point, this one I believe is a 40, this one's a 60. We have a hole here, so it is limited. Like there's not a huge difference between a 40 and a 60. And if we had a 80% groove, you wouldn't see much difference either. So that's like the downside. But in a case like this, knowing that you're almost at 60% the signal strength, you would want to go back into this tube with an iris probe or even a borescope just to get an idea of what's going on. So this is a real tube that we got data from. And as you can see, this is just complete pitting all over the place. So on the absolute, not much to be seen on the absolute, but on the pit, we're just going nuts. So this is, it's easy for me to say that because I saw the tube. It's somewhere here and it's pretty banged up. A lot of ID pitting, but this is what a signal will look like, right? So at a certain point, we had fun just putting pits all over the place, but between you and I, you could have put a cursor here and a cursor there and just wrote a giant pit, and be like, not much to do. Okay. Then I will show you a single. All right. So the single exciter, Rft. So now we're in carbon steel. So this one only has pits, and that's what we see here on differential. We see the pits. We have one, two, three, four, 5 pits. So we can go here and we see them very well. And by very well, we mean over here, right? So they're all there. 20, about a 40, a 60, an 80, and a full hole. So in this case, what we do is we calibrate the hole at 90 degrees, 1 volt, and everything else just flows from there. Okay. So that one's not too hard to look at. If I go dual exciter, because I'll show you the comparison now. So same tube. So still pretty good. We're able to get good separation between our pits. So that's good. Once again, 90 degrees, 1 volt. So that's pretty good. So as you can see, there's not a huge difference between a dual exciter or a single exciter for this. If I go into a single short defect, so short meaning that the defect is shorter than the probe, right? So the defect is less than 2.5 times the OD. Okay. So what we have here is we have just basically you have the exciter. You have the exciter and the pickup, right? So you have 2 pickups. So you have one pickup that sees it first, and you see it with the exciter, which is why you have 2 bumps. So it looks like camels, but it's actually 3 different defects of the same length, just different size, depths. And here, what's interesting, this is the RFT curve, and what that does is it can actually tell you if it's on 360 degrees, 270, 80, or 90 degrees of the material. All right. So in this case, I know for a fact it's on 360 degrees. And we know this because it's touching the back line. So this would be 360, this would be 270, this would be 180, this would be 90 degrees, right? So if I have something that's only 90 degrees, well, my signal would stop around here. If it's 180, the signal would stop around here. If it's 270, it stops around here, and then 360. So right now, it's kind of in between both. Okay, like I said, this is where the inspector game comes in, where you're like, well, I'm pretty sure this is 360, so I'll mark it as 360. Okay. And if I go on the bigger one, you can see we get pretty close. Now we have 2 bumps because of the exciter and because of the dual pickups, right? 2 picks are picking up at the same time. So we have this going on, okay? So let's look at the same tube, but now with a dual exciter short. So now the distance between the defects is shorter than the length of the tube, length of the probe, okay? So what we have here is we have the first defect, which we still have double bumps. However, then it starts to merge with the other defect, and then the other defect merges with the other one, and then before you know it, you're almost like merged together in a sandwich. So this is where it gets a bit more complicated for the analysis aspect of using a dual exciter probe. It gives you a great, I mean, the signal's clear, everything's fine. If you're going around a support, you'll get both sides of the support. But if all you're looking at are short defects and there's nothing around the support, and this is because as an inspector, you know what you're looking for, this might not be the best probe, because then it makes your analysis harder. Okay. And we're going to look at the long. So long defects, so as I said before, head and shoulders, right? So shoulders, head, shoulders, head. So this is relatively easy to look at from a TRS point of view. It also creates, like from here to here, I'll back this up. It also creates what we call the dog leg. So what's going on here is you have a long defect and your entire probe fits inside that defect. So this is when you have the coil and the pickup coils are in the defect. The exciter is still out. Okay, so this is the first leg. This is when everything is under the defect or the damaged area. So it creates like this dog leg, hind leg. And then when you come back out, so now the pickups are leaving the defect zone. Now your exciter is only there, and then everything's out. So this is what's going on. So pickup, then we have pickup exciter, then we have exciter, and then we have everything out. Okay, same can be said here. And if we look at the dual exciter long, we have the same thing, the same almost problem as we saw before, where there's some merging together. So here we have basically one exciter. Well, we have the pickups. We have the pickup exciter. We have pickup exciter pickup exciter pickup, and then we're losing one of the pickups. We have exciter pickup, and then we just have pickup, and then we're back down to zero. So we kind of get like this, what I call the toupee, right? The extra bump here because of the fact that the entire defect's so long that the entire probe fits inside it. So you kind of see the wall loss, not once, not twice, but 3 times, which is why you get like this little extra bump up here. Okay, but technically your defect, it's only this deep, right? Which is still pretty deep, right? Because as soon as you're up here, you're getting both. You're getting it twice, the wall loss, but that's not the case. You only want one wall loss. It's just that because the probe fits inside it gives you double, and because the entire thing can fit inside that defect gives you triple. So, like, yes, this one is worse than this one, but it's not like 100%. I mean, we're not bursting through this tube. We're maybe at 40% here and 20% there. Okay, so that's RFT, NFT, MFL. So the way that we look at different signals. And I'll just load up one last thing. And then we have the ECA tube C-scan available with a TXE probe. Let me just load this one up. So once again, this is eddy current. However, we get like these wonderful little images here. So we have a mixed channel as well. So the mixed channel is interesting because right here, we got rid of the support, which is right there, not here, there, not here. Actually, it's even there, not here. So, we get the same type of well, the physics stay the same, right? The physics can change just because you're using an array. It's eddy current, and we kept that in here. So it's pretty interesting that you can get a nice color image that you can rotate around here, and you can play around with it as much as you want. And in some cases, it might be easier to show a client or a superior who doesn't know much about eddy current, because this is easy to analyze. I think you can I see defects. I can only see the height. That's fine. And then if I bring back here, if I load the same cal tube, and then I can tell my boss, hey, by the way, there's a hole here. They might not believe me as much. Okay, so look, I've been talking for a long time. I hope you've enjoyed it. I will stop sharing my screen to get back into the main here. And yeah, so I'm just wondering if you have any questions, anything, if you got anything else to talk about, or I'm here. I got time. I got to use 2 headsets for some reason, but I can hear your questions this way.
We don't have any other questions at the moment. we'll just give everybody a chance to, if they want to ask any more questions here. In the meantime, just a reminder for everyone that the recording of this presentation will be available on the home screen afterwards, so you can go back into Crowdcast, access the recording of this video and the presentation. As well, if you have any questions afterwards, feel free to reach out to your local Olympus representative. I don't see any other questions coming up at the moment, Terrence, so
no problem.
Thank you very much.
Cool. And if you have any questions, like Graham said, feel free to contact us at Olympus. We love talking to people, so that's that's what I've been talking an hour and a half. All right. So no more questions, Graham. I'll let you decide.
No, it doesn't look like there's any more questions. So thank you everyone for joining us today, and really hopefully look forward to hearing from you. Thank you.
Take care. Bye.